Okay, it's my pleasure today to introduce Professor Karim. Professor Karim actually used to be my old colleague when I was a professor at University of Waterloo, so I know him quite well. Karim is a very distinguished professor at the University of Waterloo. He started off getting his bachelor's and PhD at the University of Waterloo, and then he moved to the Simon Fraser University, where he was on the faculty there for 5 years. But I guess Waterloo liked him so much, they said that come back and become a professor at Waterloo. So he's back at Waterloo. He's a unique individual because his work spans a number of areas, going all the way from materials into devices, into circuits, and systems. Typically we professors work on materials, or we work on devices or circuits, but he spans the whole arena over there. Currently, his work is on building low-cost imaging systems with a focus on medical applications. So that's what his current focus in his group is. And he's also an IEEE distinguished lecturer from the Electron Device Society. So Karim also has recently founded a company and is the chief technology officer of that company. The company is called KA Imaging Systems, which is making the images, at least some of the images that he's going to talk about to us today. So with that, I'd like to welcome Karim to the University of Washington.
Thanks very much. So thank you, Anand, and thank you to the department who invited me and everybody who arranged for this seminar, and thank you to all of you for coming and listening. So as Anand said, I've been at Waterloo probably for 9 years now. And my work goes in two parallel streams. One of them I'm going to talk about today. This is the part on these diagnostic X-ray images. The other part that I'm not going to talk about today focuses on very high spatial resolution images. And if you're interested, you can ask me about that later. But today I'll just focus on this, on the story of the low-cost X-ray imager. So I'll go through the acknowledgments. So this work that I'm going to talk about, it spans probably, I would say, 16 years of effort. So there's a nice story that, there's a bit of a backdrop, and then you can see where it's kind of ended up. It's about 16 years of effort. There's a lot of people who've contributed. I just took one photo from a random shot in the last 16 years, and it includes, I think, many of the people who were instrumental to making this work successful. So that's my research group. That was probably the fellow standing in the back there. Let's see if I can find him on this cursor. This fellow here is the guy who actually ended up being the last person to touch this work, and right before it was translated into a commercial product. But there's a lot of companies along the way, a lot of institutions along the way that actually made this happen. Now, what I'll talk about today is I'll give a little bit of a background on X-ray imaging, particularly for underserved populations. Then I'll talk about why is digital the ideal way to do things. I'll get into a little bit of the technology with regards to the pixel architecture, as well as the circuits, the sensors, and I'll summarize. So what's the story on digital X-ray? Turns out 2 billion X-rays are taken every year to diagnose some kind of a ailment, okay? And that's just in the medical space. We're not talking about X-rays that are used for inspection, for security, for non-destructive test, for quality control. We're not talking about that. We're just talking medical. And just in medical, you have 2 billion X-rays taken annually. So that's pretty interesting. That's like 1 X-ray for every 3 people on this planet. 300 million of those X-rays were actually taken in the US. That's a 2012 figure. And the entire industry, as far as the medical side goes, with regards to X-rays, is worth about 10 billion. So it has some big impact, actually. The reason people like X-rays is it lets you see inside an opaque object, and it helps you maintain the resolution, the spatial resolution. Those are two very important things. And of course, you can get the image in a reasonable amount of time. So for example, if you talk about diseases, X-ray is most predominantly used for things like lung disease, like tuberculosis, which is it sometimes manifests itself in the lungs. You've got pneumonia, you've got chronic obstructive pulmonary disorder, COPD, on pneumothorax. It's also good for fractures, orthopedic kind of uses. Of course, interestingly enough, people go into their doctor's office with a small cold. The doctor says, go get a chest X-ray. And when the doctor looks at the chest X-ray, there's a realization that there's cancer involved or cardiac disease involved. So chest X-ray inadvertently also helps diagnose cancer and cardiac disease. Okay, so it's a very, very versatile modality. It's kind of a workhorse. You can get good value out of a doctor if you don't have X-ray technology available. Now, how do you actually take X-rays? The most common way is a film screen. This is literally outdated in North America. You don't really see many people with film screens out here. It started out in 1896 with Röntgen, right, discovering that the Crookes tube that he had in the lab actually was causing this invisible radiation to show up. Anyway, if you go after film screen, they're very inexpensive systems. They're still used, actually, all around the world, just not in the US or in Canada. But you do see them in India, you see them in Africa, all over the place. And the reason you still see them is because it's very inexpensive to get into. It's a very cheap entry point, to maybe a $15,000 to $25,000 price to buy a little system that can do X-ray imaging. The challenge, of course, is not the entry point. The problem with film is just like in the old days with photographic film, it's the consumable. So you have to worry about having to pay for the film, pay to develop the film, store the film, right? All the workflow that goes around that. 1975, the first quasi-digital X-rays appeared. It's technology called computed radiography. It's based on something known as a storage phosphor. It takes a material, a phosphor, and that phosphor, when X-rays are shone onto it, charge is stored inside it. You can read the charge out of it by scanning it with some kind of a laser of a certain wavelength. The neat thing there is, of course, now I don't have a consumable, right? I don't have film, or at least my consumable is a little less consumable because the plates last a lot longer than just the single-use films. So their entry point is a little bit higher because you need this reader technology, so it's $35,000 to $60,000. The plates are fragile, so that's one issue. But the main challenge with CR is it doesn't have the same quality as film. Film actually has better resolution and better dynamic range than most CR. Most people don't realize that. But CR is still easier. The workflow is much better, so it's still quite dominant. And then in 2000, much like digital photography replaced film photography, digital X-rays came upon the scene. So that's when I actually first got introduced to digital X-ray. In fact, I started working in this field in 1998. So at the time when I was working in it, I was a graduate student, there was no commercial digital X-ray imager available. And in 2000, the first one was introduced. It was it was received actually surprisingly with a lot of interest because of the improvements in workflow, but it was very expensive and not robust at all. Over the years, the price has changed quite a bit. Today, you could probably get a decent chest X-ray system for anywhere between 70 and 150,000 US. There's no consumables. It's just like your digital camera, right? The image is instantaneous, just like your digital camera. It's fully compatible with teleradiology, and what I mean by that is you can email the image, colloquially speaking, to a doctor who doesn't have to be in the same location as you are, right? So then you can get a diagnosis remotely. If you think that's surprising, consider that this is routinely done in the United States. In a large number of cases, images, CT scans, MRIs are actually shipped overnight to India. The diagnosis is done and it gets back to you in the morning. So teleradiology is actually a very powerful feature of the digital revolution. And the image quality is very high, actually. It's competitive to film, and in some cases, it's better. So that kind of gives you an idea of what digital X-ray exists and what are the options out there and where the issues come in. Now, let's talk about specifically what are the issues with X-ray imaging around this, right? So the big issues come on quality. Quality is primarily affected for film and for CR, not as much for digital. The reason I would say that is in the case of film, it's critical, just like in photography, if any of you still maintain, a touch with photography or working in dark rooms, there's an art to developing film, right? You need to keep the developer at a certain temperature. You need to know how much developer to use, right? So that doesn't happen in many places around the world, that type of quality control on the film. So that usually, even though film in the ideal situation is better than the other modalities, like CR, in practice, it doesn't turn out to be that way, right? And the other issue that affects quality is if you don't have a doctor around, and if you're not using teleradiology, then your diagnosis is only as good as the doctor. You could have the best X-ray out there, but if the doctor is unable to read it, then you've got a problem, right? So that's where the quality issue comes in. Access is the other issue. Again, it's not an issue in North America because the supply chains for developer, for the film, for replacements, they already exist. But in places like India or particularly in rural Africa, you don't have that. Okay, the supply chains do not exist. And so it's hard to get the equipment, new developer, refrigeration, whatever, in place. So that's going to be an issue. And also at the same time, patients sometimes can't get to the facilities that have all the infrastructure in place. So that's an issue, again, with film and CR. Digital, not as much. And then the cost, that's the main weakness of the digital technology because it's so esoteric and so unique. The cost is still quite high, right? $70,000. Again, it's not a huge number in North America, but overseas, that's a limiting factor. It's difficult for people to be able to overcome that initial capital cost hurdle. And because the cost of the system is high, then patients who get charged, the cost per test also gets driven up, and that makes it difficult for people to make that move. So that's why, in a sense, the adoption of digital X-ray is kind of stalled to some extent. You don't see it happening around the world. We had it happen in North America, but we don't actually see it happening in Africa and Asia. In fact, what you see out there is CR technology seems to be filling in the gap, and they are marketing it as quasi-digital. Now, this is where we kind of come in, right? We've been working with this field for a long time, and so after about, I'd say, 10 years of working in the field, I finally came upon an epiphany to me at the time anyway, was we got to bring the price of this thing down. So far we've been pushing performance, but now it's time to actually bring the price down because that's going to accelerate adoption, and then the technology becomes actually more impactful. So our goal was that we were going to come up with a digital X-ray diagnostic system for the initial price of film X-ray, but the benefit, of course, is there's no consumables in digital, right? With film, you have consumables. That's what drives your cost of ownership up, but with digital, you don't have that. So this was our target, $15,000 systems using digital. Let me give you an idea of what a digital X-ray system would look like, okay? So here's your X-ray source. Right? You can, like these are pretty common. There's not as much confusion as far as they goes. The detector is the key component in this, right? It's a camera. It's not a camera like your cell phone camera. The cell phone camera occupies a very small area because the lens is used to put the scene, to take a large scene and kind of compress it down onto the camera surface. With X-rays, it's not cost efficient to focus the X-rays, so it has to be projection imaging. So the size of the X-ray imager has to be the same as the size of the object that is being imaged. So if I'm going to image somebody's chest, then I better have an X-ray imager the size of that person's chest. Okay, so these panels are large. Okay, like when you look at the panel, it'll be like this big, 45 by 45 centimeters, or if you like it in inches, 17 inches by 17 inches, right? That's what it'll end up as. And then, of course, you have a computer or a tablet or something sitting there. So the X-ray source turns on, the patient is imaged, the detector captures the image, and the image shows up on a computer, and then you can do with it as you wish. You can store it, you can ship it out, you can email it, you can try and diagnose it right there. That's kind of the overall system architecture. Now let's get into a little bit more detail as to what's actually happening inside the detector, right? So when you look inside the detector, I've taken a cross-section of the X-ray imager. Okay, so this is where we get a little bit technical. What you have here are two basic devices at each pixel. It's a pixelated device, much like your digital camera. You hear 10 megapixel, 18 megapixel camera. Well, digital X-ray images are just like that, 9 megapixel, 12 megapixel, so on and so forth. At each pixel, you will get a sensor, a light sensor, and a transistor. A transistor, of course, is just a switch to take your signal in and out. On top of the light sensor and the transistor is the scintillator layer, okay? So X-rays come in, they strike the scintillator, light is generated. That light is then sensed by the sensor. It's a photodiode typically. That photodiode generates some photocurrent that's stored on the capacitance of the photodiode, and then at some point you flick the switch on and you take the charge out. Okay? That's how that technology basically works. This is the most common way of making a digital X-ray camera. The challenge with this particular process, right, or this particular architecture, if you will, is that the sensor is very, very specialized. It's not the PN photodiodes that you see in your silicon process, your CMOS silicon process. There's a reason why silicon is not actually amenable to making large area X-ray cameras. The main reason is you can't make a 17-inch by 17-inch plate because your wafer is limited to typically 8 inches, especially for the image sensor processes. Now, you could try and get the 12-inch wafers, but they're not easy to access for most camera manufacturers, and the intricacies of the business don't make it feasible for people to actually go and buy out wafers in a 12-inch fab. But the 8-inch fabs you can access, but then you get these little pieces like a 6-inch tile or a 6-inch by 4-inch tile, and then you got to have like 10 or 20 tiles. And that, just trying to make a device that can withstand temperature, heat, humidity, shipping, storage, it's quite a difficult task. So what they do is they use a technology known as amorphous silicon, which is the same technology that you see in your laptop screen, and they make a photodiode in that, right? Out of that. Now that photodiode happens to have a p-doped contact, an ITO layer. It's a little bit specialized. So you can't just go to any TFT fab and say, I want this to be made, because some of those layers introduce contaminants. So it makes it a little bit complicated. So the price actually for these panels drives up because everybody who makes panels like this has invested a lot of money into making their own facility for photodiodes, okay? And they want to recover that sunk cost. And on top of that, that same facility has to be operating year-round. So there's an operational cost that goes with it. So that drives up the actual price of the panel. Because the price of the panel is high, not many people want to commit to buying it, right? They'd rather buy film or they'd rather buy CR technology. So the volumes remain low and you end up with this chicken and egg situation. You've got digital where if you had high volumes, you could drive the price down, but because you're still trying to recover your sunk costs and your operation costs, you're not able to do it, and so you're kind of stuck in limbo, right? So that's your indirect detection, okay? Scintillator, photodiode, and switch. Now, you could take another route that has been tried by some manufacturers. It's what they refer to as direct detection. What happens there is you use a photoconductor. It's basically a thick semiconductor, typically high band gap, because they want to keep the dark currents low. And X-rays strike that photoconductor, and they generate charge. And that charge is then collected on a capacitor, and that capacitor is then, the charge is taken off that capacitor via a switch. Okay, so it's just like indirect detection, but the difference is you don't need a scintillator. You actually use a direct photoconductor for that. Now, in this case, when it first came out, hypothetically, people said that the manufacturing cost should be lower because we don't have to worry about the pin photodiodes. And so we don't need our own facility to make the thin film transistor, right? The switch and the photodiode. All we need is a smaller facility to make the selenium photoconductor. Okay? And selenium photoconductor is not so uncommon. Xerox used it in photocopiers for 20 years, right, from 1970 to 1990. But you still do need that specialized selenium process, right? And there are some other issues with selenium which have to do with reliability and temperature sensitivity. So for that reason, to this day, the volumes in selenium have remained low and the prices are still high. Okay, so this technology didn't pan out as well. So let me get into now a little bit more about the architecture of the X-ray camera, right? You've kind of get the overall idea of, well, how you would detect X-rays. Now let's talk about what's happening on the pixel array. So remember I said it's a camera. So this is an XY matrix sitting right here. Okay, that's an XY matrix. Each pixel has the sensor, like I said, and a transistor switch, right? There's a whole bunch of rows. So when you send a signal on one of these rows, the data for each of these pixels is output on the column, and it goes out to an amplifier. Okay, and there's an amplifier for each column. So if I have an array that has 4,000 rows by 4,000 columns, then I would need 4,000 column amplifiers, right? One amplifier per column, right? That's how it would work. And then you multiplex it, you run an A to D, and you take the signal out, right? So at each pixel, if I was to draw a circuit model for this, I would get my photodiode, right? That's the sensor sitting here. That capacitor could be an external capacitor, or it could be just the capacitance of the photodiode that we've modeled. And then you have the transistor switch that you pulse, and the signal from here is driven out to this charge amplifier on the column. That's how the vast majority of X-ray imagers today work, right? Using this particular architecture. It's known as the passive pixel sensor. It has a history in actually CMOS technology, because CMOS technology used this in the 1970s. But then they didn't stick with it for a variety of reasons, not least being that the column charge amplifiers are very expensive. Now, what are the challenges with this particular PPS architectures? Well, one is you need lots of charge amplifiers. So the charge amplifier is actually a cost driver for you. Two, the charge output of the passive pixel is not suitable to multiplexing. And multiplexing is important if you want to drive costs down. And then lastly, the noise, the electronic random noise, stochastic noise that is generated on each pixel, it ends up driving, it ends up drowning out the minimum signal for some modalities, like in fluoroscopy. So it also ends up affecting your performance. There's a performance problem in this technology as well. Now, years back, this is probably back in like 2001, 2002, we suggested, this was actually part of my PhD work, that why don't we try and build a pixel-level amplifier in amorphous silicon technology? That was actually one of the things we suggested. And it was revolutionary at the time because amorphous silicon is a amorphous material. It suffers all the problems that all amorphous materials do. There's lots of traps in it. There's problems with mobility. It's about 1,000 times slower than, say, silicon. And the lifetime of carriers is minimal as well. Okay? So when somebody comes along and says, let's build an amplifier, an analog circuit, and amorphous silicon, it's a little bit unusual. But this is what we tried. The biggest challenge we ran into with amorphous materials in building an amplifier was not so much the gain. It was actually the timing, the speed of response. Everybody at the time had an idea that we should be using a voltage mode amplifier. And what I mean by that is the amplifier is driving a voltage on the output, okay, a voltage mode circuit. So my kind of different way of doing this was I switched it to current mode. The problem with voltage mode was the resistance associated with each of the switches, the RC time constants were too long. So anytime you tried to build anything that would respond in a reasonable amount of time, it would take forever. But when you switch to current mode, you get rid of that problem. Okay? So we actually introduced the first class of circuits for amorphous materials, current mode circuits, and they actually became the de facto way of making circuits in amorphous materials. Okay? In fact, OLED drivers were using current mode circuits as well shortly after we did this work with active pixels. current mode active pixels. So here's a simple circuit that we had tried years back. All you see here is a reset transistor that is used to reset the sense node. This is where the photodiode would sit. Okay? You have an amp transistor, which is nothing more than like a source follower. And then you have a switch that controls access to the column. And then the signal, or in this case the current, is driven directly into a charge amplifier. That's why it's current mode. So the current that comes down this line goes and charges up the output amplifier. You can actually use very simple physics to figure out just Q is equal to VC. You can figure out the relationship between the charge on the output and the charge on the input, right? And the key factor controlling that relationship is time. The longer you integrate, or the longer you leave this capacitor charging, the larger signal you get. So your gain, the charge gain, if you will, is a function of your sampling time. Okay? That was kind of the neat way. So you just basically integrate the signal for a while, and you get a pretty good signal to come out of it, right? That's your charge gain. This was one of the first active pixels that we built in amorphous silicon. For those of you who like layout, this was actually made in a fabrication facility in a university. And yeah, and here's kind of a bunch of different charge gains. Okay, so all we've done here is we've played with the different pixel capacitors. So if you have a smaller pixel capacitor, then the voltage that you get on this node is going to be larger because Q is equal to VC, right? So voltage and capacitance are inversely related. So if I decrease the capacitance, my voltage goes up. If my voltage goes up, my current goes up, so I get larger signal. So the lower the pixel capacitance, the larger the gain I get out of this. Interestingly enough, the lower the pixel capacitance, the lower the electronic noise, the stochastic random electronic noise of the pixel as well, because the key component to noise is reset noise. It's basically the switching noise of this reset transistor. That's what gets sampled on this capacitor right here. Right? So this was a very interesting insight that came. And then, of course, we did some scaling exercises, and what we discovered is that you could actually make a pretty decent amplifier if you actually had access to a reasonable commercial process. At the time, we didn't have access to a reasonable commercial process, so we just did an in-house process, and it was a decent amplifier. It wasn't a great amplifier, but it actually was enough to prove the concept. Now, one of the challenges that comes with active pixels versus the passive pixel architecture is that instead of one transistor per pixel, you've got 3 transistors per pixel. And this is not so straightforward because in amorphous silicon technology, the transistors are a little bit larger than you see in CMOS. In CMOS, they might be in the submicron range. In amorphous silicon, we're talking 5, 10 micron type gate lengths, okay? And the gate width will be even bigger than that. So if you put 3 transistors on a pixel, that's going to consume a lot of area. Now, if the transistor consumes a lot of area, you don't have as much area left for the photodiode to absorb the light. And what that means then is you lose your light sensitivity. So that kind of ruins the whole point of putting in the amplifier because you were trying to boost the signal, but now you're going to lose it. So one of the things we explored early on was instead of having the photodiode and the transistors in a coplanar fashion side by side, said, well, what would happen if we put the transistors underneath the photodiodes, right? We bury them under the photodiodes. Now, this is not as easy as it sounds, okay? I mean, it's easy for me to draw this little picture. It's a lot harder for me to actually build that type of circuit, not least the problem being that some of these layers, these interface layers between the ITO and the amorphous silicon are very thin. They're in the 20 nanometer range. Any kind of step coverage variation is going to cause all sorts of problems. The device just won't function, right? But you could do this. You could try this coplanar type architecture. You could try this buried transistor architecture. And so we did. We actually built some devices with that very carefully, right? And we were able to actually get these devices to work. One of the accidental problems that came along in trying to bury transistors under the photodiode was with amorphous silicon, the substrate is always floating. You know, in crystalline silicon, the substrate is typically grounded, so you don't have to worry. With amorphous silicon, because it's a thin film transistor, the substrate tends to float. The problem with that is if you don't shield the substrate from the impact of errant biases, your transistor will just start to conduct when you don't want it to. So one of the things we realized when we did this type of burying action is it made the process more complicated. We had to come up with a shielding metal to protect the amorphous silicon semiconductor from becoming conductive, especially when we didn't want it to be, right? So this was one of the experiments. We actually built this structure. It's quite a complicated structure, but it's got a dual gate amorphous silicon, one on the top, one on the bottom. The one on the top is just a shield. And by playing with the biases on the shield, you can control what the leakage current in the device is going to be, right? So once we figured this out, well, we knew we could do it. It was now more of a manufacturing challenge, right? That's what it was. Now, the other problem you run into amorphous materials is because of that entire defect profile in the semiconductor, you have an issue with traps. You have an issue with deep state traps, which are in the bulk, and you also have an issue with shallow state traps, which are on the tail, or on the edges of the band gap, right? So in this case, for example, here you've got deep state traps, and then you've got some more traps sitting near the conduction and valence band edges. The impact of that density of states diagram is simply, if I operate a transistor and I put a gate bias on that transistor, the threshold voltage of that transistor is going to shift, and the subthreshold slope is also going to shift. And when you think about that, you're like, this is going to be a very difficult device to work with. How can you do anything with a device where the threshold voltage is continuously moving just by using the device? Or the subthreshold slope is changing just by using the device. So here's one of those experiments we ran. We put 15 volts on the gate for 3 hours, and you can see the threshold voltage shifted by almost 1 volt there. And then you put minus 15 on the gate for 6 hours, and the voltage shifts back, right? So you can have this kind of interesting reality. And the funny thing is, when people built these LCD screens that you're used to seeing in the old days, this is a problem they had to contend with as well. That's one of the reasons they went to the switch-based architectures. They stayed away from anything that was complicated. Anyway, we came up with some models to determine it. The saving grace for medical, and this is actually better than in the display field, the saving grace for medical is that the duty cycles in the medical application are a lot smaller than the duty cycles in displays. So for example, if you talk about a megapixel array for a camera, you're only really turning on a row of transistors once every, say, 1,000 or 4,000 times. So your duty cycle is like 0.1% or like 0.025% or something like that. It's tiny, okay? Because the duty cycle is small, the impact of the VT shift is not so bad. So when we actually did the modeling and measurements on our active pixels, what we found is that, yeah, you get some degradation, but actually there's some kind of a compensation that kicks in. So the degradation is not continuous. It's not going down all the time. It actually saturates after about, say, 1,000 minutes or something, right? So this was quite a relief as far as we went. And then, of course, we said, OK, well, that's what's happening to the VT shift. How is the gain of the pixel varying because of this? And again, at a duty cycle of like 0.1%, the gain is, it kind of stabilizes after a while. If the duty cycle was 10%, it wouldn't be stabilizing. There'd be some major issues, right? So this is quite an interesting realization that came to us when we were trying to make this thing work. Now, the last surprise that we had when we were trying to get these active pixels to fly was this random stochastic noise that I was talking about, right? Like random noise in the pixel. And what I mean by random noise is the classic noises that come with any kind of semiconductor device. The thermal noise, the shot noise, the 1 over F or flicker noise. Those are the ones those are to be expected. Okay? So flicker noise, for example, in an amorphous material, a device made using an amorphous material is typically very high because the density of traps is very high, okay? Like the density of trap states. Thermal noise is not too bad, but the flicker is usually where the problem is. So that's what you see here. You can see like measurements we had done on the noise with various gate biases, and that kind of shows you how the flicker noise was varying, right? A noise that came as a surprise to us, I mean, we expected this based on experiments that had been done with CMOS technology in the past, but the numbers we measured didn't actually match up with what the theory was saying, was this business of reset noise. And reset noise, remember, is nothing more than the thermal noise of the reset switch sampled on the pixel capacitor, okay? That's what that noise is. Now, this is a measured power spectral density of that reset noise. I could probably spend half an hour and tell you how we did that measurement. It's such a complicated measurement. But the neat thing was we did the measurement, and we actually were able to see this power spectral density. But when we actually crunched all the numbers, the input preferred noise that we calculated didn't actually match up. And what we realized is that in the classic reset noise analysis, everybody assumes a switch that has a very minimal on resistance. That's not true with TFTs. The on resistances are in the mega ohms, so there's some correlations that kick in. So then we had to go back and try and figure out what actually happened, and then we did some modeling on it, and we were able to actually get a pretty good model for that reset noise. Anyway, we take all the noise, we summarize it, right? And we were able to calculate what an input preferred noise would be. So for example, with a pixel capacitance of 1 picofarad, and a gain of 13.3, remember this is in the industrial commercial type process, you could get an input preferred noise of about 630 electrons. Now that's not bad. 630 electrons is actually pretty good because it allows you to work with fluoroscopy, which is kind of the toughest medical modality because that's real-time imaging. So this was very pleasant. We kind of said, okay, active pixels can work, they can give you performance, and obviously they're going to give you all sorts of other benefits like multiplexing, which drives your cost down, so on and so forth. So here was one of the first active pixel arrays that we built. Instead of a 1 megapixel by 1 megapixel array, we built a 2 by 2 array. It's only 2 pixels by 2 pixels. That was the first one we ever did. That was quite difficult to get working. And we used a selenium conductor on top instead of a photodiode because the selenium was easier to access for us. Somebody we knew could deposit it for us. So we made the electronics, we made the transistors, we fabbed it all, and then we sent it off to our friend who put the selenium on top. And we got some decent results, right? We did actually the whole chain. We got the pixel, we got the column amplifiers, we got sample and hold circuits to do correlated double sampling, right? And we were able to get some pretty good results. And what we found is that our models were actually pretty good at predicting what the performance of that active pixel was going to be. In fact, the first array we built, our input preferred noise was around 3,000 electrons, which is not bad for a first try, okay? Which wasn't too bad. And the reason this noise was so high was primarily because the pixel capacitance was 3 to 3.5 picofarads. We couldn't get it smaller because of the process, the in-house process that we were using. Now that was a while back, right? In doing this work, I mean, that work probably took us a good solid 5 years, right, to get through all those experiments, the reset noise, the metastability, all of that. But one of the realizations that came out of that entire experiment was exactly the point that I raised about the pixel capacitance, okay? The C-pix of being 3 to 3.5 picofarads. If you can't push that pixel capacitance to 1 picofarad or less, your active pixel is not going to work because the charge conversion gain is going to be low and your reset noise is going to be high, okay? You're going to get affected from both sides. So we knew if we went down the path of the PIN photodiode that I had been talking about, the one that everybody was using, you were going to have a problem because PIN photodiodes, it's basically a parallel plate capacitor. So the capacitance is high. It's typically in the 1 to 6 picofarad range. In fact, for most commercial devices like a fluoro or something, the capacitance could be as high as 6 picofarads. So active pixels with a PIN photodiode would be very, very hard to get working, okay? And on top of that, the process was proprietary, so there was a cost driver that we didn't like. So we had to think about using a different sensor that had a low capacitance. That was the first conclusion we hit. I think it was probably 2004 or 2005. We knew that was important. So what we tried was, we said, why don't we, instead of focusing on PIN photodiodes, where we know we're not going to be able to get the performance we're looking for, why don't we look at the selenium option? And selenium was also a commercial material. It was already out there. People were using it. Yes, it wasn't as cheap as the PIN photodiodes, but still, I mean, it was available. And it had, most importantly, the selenium layer is very thick. It's like 1 millimeter thick. So the capacitance is tiny. You can control the capacitance to whatever you want, so you can get good gain. So we said, OK, why don't we build some devices using selenium? So this was work that we ran probably between 2005 and 2009. It was about a 4-year effort, 4 or 5 year effort. So here's another active pixel sensor design. This one's actually a 4-transistor active pixel sensor, not the 3-transistor. We added some additional functionality to increase the dynamic range by putting in the 4th transistor. And we worked with a company based out of Montreal in Canada. They were eventually bought by a US company called Analogic in Boston, and they put the selenium on for us. So we built the transistors, we again did the pixel circuits, they put the selenium on for us. And here's what it looked like. Okay? You have a glass wafer with the imaging array on it. You've got all your support electronics like the charge amps, the frame grabbers, computers, gate drivers. And then you've got selenium with a encapsulating layer of parylene and a high voltage contact. So that's what the imaging array looked like. It was tiny. It was like maybe an inch or 2 inches in size. And here was an image we took off that. And what I like about this image is I've compared here a commercial device that's sold by Toshiba. Okay, it was the Analogics FPD14 sold by Toshiba with the image that we got from our active pixel detector. Okay, the amplified pixel detector with selenium. And it's quite comparable, actually. Our pixel pitch was better than the commercial one that they sold, and the SNR also turned out to be better, and I'll show you, and I'll show you what I mean by that. So here's the SNR results. The red is the FPD14, the commercial device. The green is actually the amorphous silicon with amorphous selenium using an active pixel, which was our device. And so we had a pretty good bump up in SNR. And again, this was using a university lab, right? So the transistors were not optimized. So we knew this was going to work. This was actually so exciting. We did some calculations on electronic noise again, because the application we were thinking of at the time was fluoroscopy. And what we figured out is with our newer designs and optimizations, we could even get the electronic noise down to around 400 electrons. The challenge we ran into with this particular technology was again something unanticipated. One of the issues we saw was on the spatial resolution on the modulation transfer function. In this device, what we had done was we had built, so this is the transistor, this is the selenium right here, and this is the back electrode. What we had done was we had made the back electrodes a little small because we didn't want to accidentally affect the transistors sitting underneath. Problem was the selenium sat here, some of the charge started to accumulate here, and it affected our spatial resolution. It started to affect our MTF. It also affected our real-time performance on lag. So in fact, that's what we saw here. This is where the transient signal starts to become very long because we had an issue with lag. And the other problem we noticed was to do with process. There was a lot of variation. We were using active pixels, sure, but the variation was huge. I mean, look at the variation on the top versus the bottom. And this is for a standard uniform exposure across the array. So we knew that that was an issue. And the gain variation was an issue. It's all correctable, but it's something that you have to take into account. But the good news is you could correct for most of it, right? And so the image looked quite good. We never went ahead with it, actually. You know, that was a very interesting one. We got to the end. We got a good result. We had a way where we could have gone forward, but we never were able to take the next step, primarily not so much because of the performance of the technology, but more because of the business case. The business case for selenium and active pixels was never very strong. The reason being, selenium was a proprietary process, so anybody who was now going to incorporate active pixels with selenium had to take on 2 cost drivers. See, if they just took selenium and they bought the TFT glass from the LCD company, it wouldn't be so bad. But the fact that we needed to change the process to active pixels, it drove the cost up. So the company actually wasn't very interested in going ahead. They said it was too expensive. The other problem that selenium runs into is it's got some issues in reliability and manufacturing. You can't operate or store it beyond 10 and 35, or it tends to crystallize. And if it goes too low in temperature, like -10, the selenium will just delaminate. So there are some other issues that we ran into with selenium, and this made it very difficult to go forward. So now we're talking 2010, 2011, okay? You can see the publication date on the work was 2012. For a while, we didn't publish it because the company said maybe we're going to do something with it. But then it became amply clear that we were not going to go anywhere with it. So in 2011, I kind of went back to the drawing board, and I said, OK, well, we can't use the photodiodes. we can't use selenium. We got to come up with an alternate low capacitance detector, right? So that's where this idea, the idea that's now kind of been translated into the company, that's where this idea was born. We looked into a new semiconductor design. It was a lateral photoconductor, or what they call gap cell photoconductors. They were used in solar cells for years in the 50s and 60s. You can use them for photoconductors. The big challenge with this is you've got two metal electrodes that are in direct contact with the semiconductor, so they give you a Schottky contact. The leakage on the Schottky contact is high, okay? So it's not the greatest. But the neat thing about this technology is it's very simple. There's no p-doped layer, so it's not going to contaminate your TFT line. There's no ITO layer on the top, so it's not going to take away your fill factor or your quantum efficiency. It can be built in a standard TFT fab, so any LCD TFT facility in Asia. The biggest challenge is how do you get the device performance to match a PIN photodiode, okay? And the big challenge that we ran into here was, well, how do we get the performance to match? And the main weakness was the leakage current because of the Schottky contact. So we innovated a blocking layer, okay, on the sensor. We actually put a layer of polyimide between the sensor and the metal contact. Now, this sounds counterintuitive because you'd say, well, you're putting an insulating layer between a metal and a semiconductor. How is that going to improve things? Because, well, the leakage will go down because it's an insulator, but how is this device actually going to function? The trick is actually in picking the right thicknesses and volume resistivities of the blocking layer versus the amorphous silicon layer, okay? So if you pick the right thicknesses, and in doing so you control the resistances associated with the polyimide and the amorphous silicon, you can actually operate the device in regions where the signal will pass through without actually charge accumulating, okay? So it requires a little bit of tuning on what thickness to pick and what material to use and so on and so forth. But the neat thing is the device functions. We tried this structure not just with amorphous silicon. I mean, to tell the truth, the structure was first built in amorphous selenium. We even tried it with organic photoconductors, like organic semiconductors, and we used different insulators. We used polyimide, we used silicon nitride, we used polystyrene. By tuning these, we were able to get it to work in almost every one of those cases, right? So this was quite an interesting insight. So now, to kind of get an idea on the performance, if I take the lateral sensor without the blocking layer, look at the difference between the on and the off current. The on current when light is on and the off current when light is off. There's almost no difference if I don't have a blocking layer. But if I put the blocking layer in, I get a massive difference. I get my 3 orders of magnitude difference. And that's very important, because that's what actually drives my quantum efficiencies up, my collection efficiency, keeps my shot noise down, keeps all of that stuff. So that was the sensor. We knew it worked, at least from an on and off current basis. The thing we were not so sure about was the device going to be able to operate at a reasonable speed, right? So the transient measurement. So when we did that, again, by the right tuning, you can get the device to work quite nicely on the transient. So here are some transient measurements for the same sensor with the polyimide layer. And again, you get the on-off currents coming, and it's quite nice, right? So we took this device forward. We built out models for it. Here's the most recent prototype that we built. It's about 1.5 inches by 1.5 inch array. And you can see kind of the gate drivers, the column amps sitting here. And that's one of the images we took off it, maybe about a month ago, or I should say 2 months ago. And that's the first image, a 150 micron pixel pitch. That's, of course, an image of a CQFP package with 44 pins around it. You're seeing an X-ray image of that. We just dropped a scintillator on it, right? So that's actually, so that was very interesting. And then this is the technology then that we transferred into the startup company that's now going to make large panels at a low price, because we finally managed to get the process down. Our near-term efforts that are still left are to do with making active pixels work with this technology, because that's going to truly bring the cost down by taking away all the column amplifiers. Yeah, that's kind of where we're going from there. So the interesting thing is, just to kind of summarize it all, you can actually build a relatively low-cost, high-performance X-ray camera using a fabless model, because you can now leverage TFT foundries all over the world, wherever they are in Asia, even in the US. And that's kind of, I think, the next generation for dropping the price on X-ray cameras, and that, of course, brings up the opportunity to put medical diagnostics in more places. And of course, it has some beneficial effects on the non-destructive tests, the veterinary industries, and so on and so forth, right? Thank you. I made sure I was watching the clock at the last. I sped up a little. Yeah.
Questions? I see EE 331 students, you know. Questions? Yeah, John.
For the device here, do you imagine using it? What are the exposure times? How long is the cycle time to actually have?
Right. So in this case, we can actually, our limitation is not set as much by the pixel sensor. It's actually set by the readout electronics that are supplied from external vendors like Analog Devices. The best cycle times they can do are, I think, line times of 22 microseconds, which translates into something like 30 frames a second for a fluoroscopy-capable 30 by 30 centimeter imager with a 150 micron pixel. Our device, like our sensor, can probably operate at like 2 or 3 times that speed. Like you would say, like the sensor response time could be like a 3 kilohertz type range. So we can go a lot faster. But the readout electronics in CMOS made by the company, they're not as fast. That's actually what the real bottleneck for us is. It's funny, we often have people tell us, oh, well, amorphous silicon is slow. I say, it is slow, there's no doubt, but right now the real bottleneck is the CMOS technology, because their amplifiers are just not fast enough for what we're trying to do.
Other questions? Yeah, Bruce.
Yeah, I realize that it's probably more a reflection on the fabrication process, but what sort of levels of fixed pattern noise do you see in these?
Yeah, they were big as far as like when we used to work in in the university clean room. When we switched into, like this array was not built in the university. This was actually built at a TFT foundry in Asia, because this was done through the company. This wasn't something that we did at, in this case, the fixed pattern noise was minimal. Like I'm showing you something that's completely raw and unprocessed. So it was really good. Like we did MTFs on this and we were quite surprised. It was a pleasant surprise. Like I would say your fixed pattern noise is probably less than 5% if you were to, you know, whereas if you were to look at the university process, it's probably in the 30 to 35% range. Yeah, it was a little worse. Yeah.
See a question over there.
So it looks like a lot of the work that you put together has a lot to do with material science as well.
Mm-hmm.
Do you have a lot of material science students working in the lab with you guys? Or
you know, it's interesting. We don't have a lot of anybody, but we do have, we do need typically one material scientist to keep us honest and to stop us from doing crazy things. So yeah, we do have one material science student in there. But one of the things that we've been able to do over the years is we've developed recipes and processes that are as close to the standard, if there is a so-called standard for the TFT industry. So that's reduced our effort in developing new materials. In fact, the material science student I have in the lab, they don't actually work on this project because this one is using very standard recipes. The material science student I have works on the other parallel path I had talked about with our ultra-high resolution, spatial resolution X-ray imager. So they're developing a selenium photoconductor and different alloys for that particular application. Yeah.
Maybe one more question, if there's one. If not, let's thank Professor Karim.
Yeah. Thank you.